Music talking for.
Okay, questions from last night's homework. Do we have any? Keegan, number one.
Yeah. Answer
So today, page 59, rational exponents, part 2. The objectives for today will be the same as yesterday. So go ahead and turn on to page 59, and we'll start our notes. So at the top, page 59, rational exponents, part 2. So rational exponents part 2. Today we're going to start by making a table that we can use to move back and forth between radical and fraction based problems. So at the top, go ahead and put radical, a line with 3 lines available, and then fraction. So under radical, when we're converting from radical to fraction, the radicand, or the number under the radical sign, or inside the radical, what does that become when it is a fractional expression? The whole number, or what's another general term? It could be a variable, right? So what's that? What could it? What do we? Term or base. So the base of the expression. So radicand becomes the base. So here we have a radical, and our radicand is 9. Over here we have a base, and it's 9. So radicand becomes base, vice versa, base becomes radicand. So these go both ways. So next, we're going to take a look at what the index becomes. The index, what does the index become? The denominator of the fractional exponent. So the index becomes the denominator and the denominator the index. So here our index, and then we have our fraction denominator. Today, this is going to be the new portion. The exponent of the radicand, or the radical, what does that become? The numerator. And vice versa. So the exponent becomes the numerator, and the numerator becomes the exponent. So this is a chart that you can use to transform between radical and fractional, radical problems and fractional problems easily, and you get the method. So let's take a look at a couple examples, and today we're going to work on solving them. So we have examples. Let's start with the cubed root of 27 x to the 6th. So we have the cubed root of 27 x to the 6th. So how are we going to translate this to fractional?
Wait, is that 6 outside or?
The 6 is just with the x. Angelina?
27 x to the 6th with 1 over 3.
So we have 27 x to the 6th to the 1/3 power? To the 1/3 power. So now we have a power with power. So recalling from pre-algebra, start of this semester, from yesterday, what do we do with powers of powers? So we multiply them. So it gets distributed to both the 27 and the x to the 6th. So we have 27 to the 1/3 power and x to the 6 over 3, because 6 times 1/3 is 6 over 3, right? 2x or what? X squared. No. So we have 27 to the 1/3 power, and as Angelina said, x squared. So what is 27 to the 1/3 power? Parker? 3. If we didn't know that, we can use our calculators and put 27 and then use that caret. So everybody get your calculators out. So we type 27 in, and then we press this caret button, or this up arrow, and that gives us our exponent, and then we can go ahead and push ND, and right now our exponent is 1/3. So 27 to the 1/3 power, as Parker said, is 3. So I only want you to use this after you've transformed it from one to the other, and when you're going to solve it. I want you to transform it, and then you can use this to solve. So I need to see the transformation in your homework before you solve. You can, and this is how you would solve a problem that has a fractional exponent. So you're going to use the caret, then the ND button, and then whatever the fraction will be. So now we have 3x squared. What if we had another example of x to the 1/3 to the 6th power multiplied by the 4th root of y to the 4th? So when you're working with variables, it's a lot easier to see how it would simplify when it's in the fractional method, right? So there's no, you don't have to change this to the radical version. Just change this one to the fractional version, because it's very easy to see that you can just distribute that 6 and multiply 6 over 3 and get your x squared, right? So we're going to go ahead and leave that the same. Now let's transform the 4th root of y to the 4th. Angelina?
Y to the 4th in parentheses, 1 to the 4th.
So we have y to the fourth, in parentheses, raised to the 1/4 power. Now we have powers that have powers, so we're going to do what? Powers have powers. We're going to multiply. So we have x to the 6/3 and y to the 4/4. And x to the 6/3 leaves us with x squared, and y to the 4/4 leaves us with y. So when working with these types of problems, when it's just, or anytime you have a variable in the problem, it's a lot easier to see how to work through it when it's in the fractional method, right? Can you notice that this is the 4th root and this is to the 4th power, and those might cancel out? Yes, but if you don't see that, or if it's a fraction or it's numbers that don't work out perfectly and cancel each other out, change it to this method and then use the power of power rule and simplify from there. So let's try another example. Let's say we had z to the 1/3 power cubed over the square root of z squared. So we have z to the 1/3 power cubed and the square root of z squared. So we're going to go ahead and solve this and then use our pre-algebra rules of dividing exponents. So z to the 1/3 cubed, what does that simplify to? Z to the 3/3. Here we have z, the square root of z squared, which is z squared to the 1/2. So z to the 3/3 is z to the 1st. And then we have z to the 2/2, right? Which is also z to the 1st. And anytime you have, well, what's our answer? We have z over z equals 1.
These questions are on homework.
Some of them are. Maybe. There are problems that look exactly like them on your homework. You'll have a lot of time in class to work on them. Let's try another one. Let's say we have 4 to the 3/2 power. So we have 4 to the 3/2 power. How can we change this? Corbin?
The square root of 4 in parentheses to the 3rd power.
The square root of 4, parentheses to the 3rd power, and our index is 2. So what's the square root of 4? Square root of 4 equals 2. 2 cubed is 8. So this is building off what we did yesterday. Now we're solving problems, and we're also going to have numbers that are not 1 in the numerator of the fractional exponents. So let's try 27 to the 2/3 power. How can we change this to a radical? Sam? How can we change this one to the 2/3 or to a radical? So 27 is the radicand. Index is 3. So do we know the cubed root of 27? Cube root of 27 is 3. And 3 squared is? How about if we had 256 to the 3/4 power? (256 to the 3/4). How can we change that? Keegan? So off the top of our heads, do we know what the 4th root of 256 is without using our calculators? So, if we don't know the 4th root of 256, what can we do? We can go to our calculators, put 256 in, use our caret, use our caret to the 1/4 power. That's the 4th root of 256, right? That gives us 4. So now we have 4 to the 3rd power, and that equals, we can use our calculators for that. 16 times 4? Yes.
Can we just divide 256 by 4? Is the same answer?
That's just a coincidence.
How did you know? 64.
Coincidence. We cannot divide exponents. We cannot use our exponents to divide the number. It just happened to work out that way sometimes. We have to make sure that we change it to this and use our steps. So 4 to the 3rd power is 64. Let's say we had 64 to the 5/6. How do we translate 64 to the 5/6? Sam? 64 is a radicand. 6 is the index. And 5 is the exponent. So using our calculators, we probably don't know what the 6th root of 64 is off the top of our head. So we have 64 raised to the 1/6 power. That gives us 2. And then we have 2 to the 5th power, which equals 32. How did we get 1/6? So, side work. We had 64 to the 5/6 power, right? Yeah. If we were to break this apart into 2 different fractions, or 2 different 5/6 into 2 different fractions, what would that be? That'd be 1/6 times 5, right? So this is our exponent, this is our numerator, which is our exponent, and this is our index and our denominator. So this is the 1/6 power. Does that clear that up? Let's try one more and then we can get started on our homeworks.
Is that notebook college rule or white rule that you're using?
It's wide rule.
Okay, just kind of figured some of them have to.
Oh yeah.
Yeah. One more. We have 1,000 or 100 to the 3/2. What does that equal? Somebody new.
I'll just answer myself. Grace. Pick Grace. Oh, never mind. Don't pick Grace.
We won't pick Grace.
Pick
Valencia?
Valencia.
What is that term called right here? The radicand. Index is 2. Three. So the square root of 100 is 10. And 10 cubed is?
1,000. You answered the question when you tried to give it to us.
It happens. Okay.
I got my answer and I just started laughing.
So, today we're going to talk about experimental probability. So today we're talking about experimental probability on page 42. Once we've got that written down, flip on over to page 36 for our objectives. Page 36, our objectives. So find experimental probability. So today we're going to find experimental probability. And we're also going to use simulation to find experimental probability. So finding experimental probability and using simulation to find experimental probability. Once we've got that written down, flip on over to 42. And experimental probability will be across the top. So page 42, experimental probability. So we're going to start off with the definition of what experimental probability is. So experimental probability is probability that is based on experimental data. So experimental probability, this is probability that is based on experimental data. So what that's saying is, as somebody has done an experiment, or we have done an experiment, to collect our data. Another definition that we're going to talk about is what a simulation is. A simulation is a model used to find experimental probability. So recently, we were talking about what theoretical probability is, and now we're talking about what experimental probability is. So we're going to go ahead and make a little chart that'll compare and contrast the two ideas of theoretical and experimental probability. So theoretical will be on our left, and experimental on our right. Go 3 down, 4 down, depending on how big you write.
4.
So who remembers how we found theoretical probability? Cameron?
Take the number possible under the favorable.
So good. So the probability of an event is equal to the number of favorable over number of possible. So that's theoretical probability. Number of favorable over number of total possible. When we're looking at experimental probability, the probability of an event happening, that is equal to number of times that it occurs. So the number of time that it occurs over the number of times that it was done. So number of times done. So we're still setting up a fraction or for representation of our data, a ratio, number of times occurred to number of times done, or number of favorable to number of possible. So the difference between theoretical and experimental data is this. So what's theoretical probability is calculated mathematically. Theoretical probability is the mathematical probability that it happens. So theoretical is calculated mathematically. So theoretical probability is the probability that mathematically something will happen. So what do we think experimental probability would be? Paige? That something might happen? So we're experimenting. Experimental probability is data that is based on experimental data. So number of times recorded. So we're actually going to do an experiment. So experimental data is an actual experiment to collect data. So actual experiment to collect data. So mathematically, the probability is theoretical. Experimentally, we're actually going to do, or an experiment will have been done for you. So on your homework, the experiments will have been done for you. We're going to work through an experimental probability in class. So we're going to look at an example of what a homework problem might look like first, and then we're going to do our experiment. So a homework problem might look like 2 players played a number cube game. So 2 players played a number cube game. The table shows the results. So once again, we're going to make a table. I did. Player A and player B. And this is the number of times they win. So player A wins and player B wins. So this is the total number of times that they won. So player A wins 1, 2, 3, 4, 5, 10, 15, 20, 25, 30 times. Player B, on the other hand, wins 5, 10, 15, 20, 25, 30, 35, 40, 45, 50, 52 times. So player A won 30 times and player B won 52 times. So now we're going to look at, once we get that written down, the probability that A won. So this experiment, or this game, has been played. 2 people sat down and rolled the dice 82 times to see who won. So how many times did player A win? Number of times that it occurs. 30 times they won. How many times did they play the game? 82 times. So there's a 30 and 82 chance that player A won. And we can simplify that. What can we simplify that to? We can simplify that to 15 over 41 by dividing both the top and the bottom by 2. So what's the probability that B won? So how many times did B win?
52 over 82.
52 over 82. So there's a 52 and 82 chances that B won. Can we simplify that? What can we simplify that down to? 26 over 41, and how did we get there? We divided by 2, both the top and the bottom. So now we want to think about, was this a fair game? Let's hear a couple responses and talk about it as a class. Was this a fair game? Player A had a 15 and 41th chance. Player B had a 26 and 41th chance. Was this fair? Somebody who thinks no. Why? Paige. B has a greater chance of winning, or did he win more times? He won more times. So that thought is correct. Cameron, what do you think? Are you saying it's fair or not fair? Cameron says it's fair. They played 82 times. Player A just happened to lose more times than he won. So the probability of rolling a dice, is the probability of rolling the dice always the same? In the game, say you're trying to get evens, or a certain number. Is the probability to get a certain number always the same? If you're trying to get 1, what's the probability you roll a 1? 1/6. Is the probability that you get a 1/6 every single time? So is the game fair? They played it 82 times. The dice, normal dice, they're not casino dice that are rigged. No, it was a joke. So the dice are not rigged. They're not going to go to a certain number every single time. It's just regular old dice played 82 times. So is this game fair?
Yeah.
Do they both have an equal shot at winning?
Yes.
They both have an equal shot at winning. B just happened to win more, right? So now, they were playing the same game, same rules, trying to get the same thing.
No, I mean, like, what if we had more numbers that?
What if B played the game more times?
No. Like, we had 5 numbers. We had 4 numbers, and I only had 2 numbers.
Trying to get?
Yeah.
They were playing the exact same game, trying to get the exact same number. It's just the idea of a game. We don't know what game they were playing, but they had a fair chance at both winning. They had a fair chance because it was an equal chance of getting the same concept. So now, we're going to work through a game of our own. So the theoretical probability. So let's say we're going to play with some dice.
Are they rigged?
No.
They're rigged.
Yes, they're rigged. We're trying to get a certain outcome. We can do evens, we can do odds, we can do between less than 3, we can do greater than 4. What do we think we should be doing? What do we want to do? We want to do probability that we get a 3? Greater than 3?
Just 3 and greater.
3 and greater? So 3 and greater. So 3 and greater. So that's what we're going to try to get. I'm going to pass dice out to everyone in the class. Do not roll the dice unless I tell you to.
Okay.
Place the dice in the top right corner of your desk until it is your turn to roll. Take one dice, pass it back.
I got 3 guys. You got blue?
What did I say about the dice? Where are we placing it? Top right corner of our desk. Are we rolling the dice?
Nope.
So why do I hear dice moving around? The dice, top right corner of our desk. I should not hear the rattling of dice.
Okay.
What? So the dice is in the top right corner of our desk. So we said we're looking for the probability that we get greater than 3. So 3 or greater. So what is the theoretical probability that we get a 3 or greater when rolling the dice? Colin. 2/3 or 4/6 or 66%. So there's a 2/3 theoretical probability that we get greater than 3. So we're going to do 3 experiments. We're going to roll the dice. We're going to have 5 people, 10 people, and everyone. So first, we're going to have Morrow, Cameron, Alexis, and Chris roll the dice one time. Roll the dice one time. So was it less than or greater than 3? So less than 3, 3, or greater. You got 4, so greater than